I realise I'm standing between you and a cup of coffee, so I'll try and go as quickly as possible. Thank you so much for this opportunity to talk to you about what we do in my lab in Seattle, Washington. We're a small team of pretty diverse scientists. Our PhDs range from chemistry and materials, biophysics, engineering, neuroscience, and so forth. But the one thing that we have in common is that we're all restless. Ever since we were kids, we've been taking things apart to see how they work and then putting them back together, trying to improve how they work. So it's not too surprising that we've all kind of gravitated to this space. We operate between where universities and research institutes predominate, which is pushing the frontiers of science, and where industrial designers and product developers work with companies to commercialize products and get them to market. We're kind of in the middle. That's not to say we don't do some of that early stage stuff or even product development stuff, but this is where we kind of live. And this is what we do. So this is what I consider the full stack, right? It starts with exploration. These are a bunch of tools and processes that we've built up over the years to dig into a problem set, to understand why current technology hasn't solved that problem, and tease it apart in a way that provides insight into what is possible, what is the invention opportunity. From there, we go into invention mode. And invention is a pretty loaded term. It has a lot of connotations. I'll talk a little bit about what we mean by invention, but the goal here is to be prolific, to come up with as many solutions, not just the solution, and then go through a process to refine and iterate those ideas. The running theme is to fail lots, right? To toss a lot of stuff out, to triage so that the ideas develop and we kind of select out the ones that our partners think are the most viable solutions. We've also got a prototyping lab and a network of contract research organisations that we work with that allow us to rapidly bring those ideas to life, right? Again, it's not what people think about. A lot of people think about prototyping, they think about industrial design. We don't do pretty, we do fast. Fast to fail, fast to get an answer about the next step, right? So this is kind of the secret sauce of what we do and how we do it. A lot of people think about invention and they think, oh, you come up with a good technology, and a lot of times that's where people end, right? And that's why there's such a huge patent literature, but not all those patents can solve the problems that industry needs, right? It needs more than just a technical solve. It has to be good technology. It has to be able to develop and solve the problem from a technical perspective, but it also has to meet economic demands. This might be different things for different problems. It might be CapEx or OpEx requirements. It might be unit cost. It might even be just the size of the thing, right? We do a lot of stuff where we've got a size constraint of the solution, or it has to fit into an existing process line without too much alteration to the process. It also has to have robust IP rights. Now, it was mentioned before, patents aren't everything, and patents aren't everything, right? But intellectual property rights are. We can't come up with a solution that is going to infringe other person's patent rights and expect that we can commercialize it. Similarly, it's going to be it's important for us to be able to deliver a solution to our partners that has a viable path to protecting those intellectual property rights so that they can be commercially exploited. It's at the intersection of all three of these that is where the commercial opportunity lies, right? And from analysing thousands of inventions over the years through different roles I've had, what we've realised is that that's an extremely rare thing, right? But you can invent into that space. You can intentionally direct efforts and iterate. It doesn't always happen on the first turn, but you can direct your efforts and iterate and come up with solutions that meet those criteria. So just a little bit of the numbers. We've analysed thousands of technologies landscapes, right? This is one thing I relish, is getting paid to study opportunities. And this is in a variety of different ways. We sometimes are asked to look at really broad technology landscapes, sometimes very specific things, but always looking for where those opportunities lie. We've invented hundreds of patentable solutions for our customers, and they've filed many patents on our stuff. One point to make here, though, is that this highlights one important factor from what we do, which is to embrace failure. To get to that roughly 250, 300 solutions that we've handed over to our clients, we've come up with thousands of ideas, right? That means we failed more often than not. And you tell that to someone and they think, oh yeah, that's great, that's bold, you've got to be brave. It's not for everyone. It's really hard for a lot of people to hear more often than not that their idea's not that good for whatever reason, or not going to go forward. It's hard to emotionally detach. I'm always astonished at how difficult it is when people start this process to become emotionally detached. And I still remember with that same emotion some of my first inventions. We've, in the lab, produced probably closer to 100 prototypes for our customers. This number of 8 weeks is kind of an interesting one, and it highlights what we mean by prototyping fast, right? The average kind of industrial design engagement is more like 8 months. Some of our projects are a day long. We get in, we get an answer, and we get out as quickly as possible. Those quick turns allow us to do rapid iterations, right? And that's really useful. This is just to show the breadth of what we do. This is a word cloud that someone generated from my patent applications recently. The first 2 patent applications that were filed on my inventions were when I was a postdoc at the Fred Hutch doing cancer research, and I think they're the last time I've ever done anything directly related to my PhD. We go into areas well beyond our traditional technical expertise. We rapidly can get up to speed and leverage industry experts to understand the challenges, to understand the problems. What we bring is that inventive mindset into it. This is a quick snapshot of the lab. I refer to it as the toy shop. It's a fun, creative space. It's an interesting blend of high science. We've got spectrophotometers and ultra-pure water systems and thin film deposition equipment, all sorts of stuff like that, next to power tools and Dremels and 3D printers. There's even a cotton candy machine in the lab, but you do not want to eat anything that comes out of it because it's had just the strangest things through it. But the point of the lab is to allow us to have that flexibility and creativity to be able to rapidly put a project together, hack a prototype and get an answer as quickly and efficiently as possible. We do use a lot of other contract research organisations, particularly if we're doing animal work or things like that require heavy equipment or things that we don't have access to directly. So just some case studies to kind of contextualize it a little bit. Pepsi came to us with non-thermal pasteurization. There's a lot of brand value in cold-pressed juice, but the trade-off is shelf life stability, right? And we looked at this challenge that they brought and thought, well, UV is really good, but the challenge with UV is that juice is opaque, and so you need to increase the amount of UV significantly, and that ends up causing the same problems as heat pasteurization in terms of breakdown and change of mouthfeel and flavour profile and so forth. So we invented a solution that was a combination of physics approaches to allow the juice to have a lot more contact opportunity with the UV chamber, together with some nanotechnology that surface coats the light guide so that it significantly enhances the UV effect. The result of that is that you can significantly reduce the UV dose to achieve an equivalent kill effect. We've done now 3 iterations of the prototype at the bench scale in our lab, and a lot of iterations in that of materials and configurations and fabrications to get to a pretty robust prototype that's now going to be handed off to product development. We're working with a large UV company. They're really excited because this is going to open up a new market opportunity. UV is typically done for water purification, so this is a new opportunity for them. Plus, they're excited to work with Pepsi. Meat and Livestock Australia. This is a crowd favourite usually. The cow tattoo. So the problem that Meat and Livestock came to us with initially was the dark cutting meat problem. Most people have seen it in the supermarket with meat that's kind of this off dark colour. It's actually perfectly fine in a blind taste test. You wouldn't notice any difference in quality, mouthfeel or taste or anything, but you see it in the supermarket and you go, ooh, I'm not going to buy that one, it looks off. And it's a significant value detractor for the industry. They've spent a lot of time and a lot of money trying to solve this with blooming agents and dyes and packaging solutions. But when we engaged, we started with that explore step. What we realised is it's not a meat problem, it's actually an animal problem. It's animal stress was the root cause of this dark cutting. And in particular, excessive stress, right? So all the animals are stressed. They're, cattle are pretty delicate creatures, and they're shipped on and off transport and in and out of lots and ultimately to the abattoir. They're all stressed, and it's really hard to sit them down and ask them how their day's going when they're coming down a gangway at an animal every 6 seconds. So what we came up with is a tattoo that we can use to sense a hormone level, in this case it's cortisol, and set it to a threshold that if they're excessively stressed, it'll be above that. And the tattoo actually visibly changes colour, so you don't need any instruments or infrastructure around it. You can identify that cattle coming down the gangway and look at them and tell whether the tattoo's blue or red. If it's red, then you triage that animal, send it back out. A couple of weeks later, you'll try it again. So we've invented this, we've prototyped it in the bench at the lab, and that's where that project is now. That same platform, though, is also being developed for real-time pregnancy analysis and other health metrics as well, and has a lot of other potential. The sludge project with the Gates Foundation is another one of my favourites, and this one highlights the necessity for integrating economics into the invention process, right? So we've been separating water from poo for millennia now, right? As long as we've been aggregating in large communities, we've had this need, and it requires some combination of time and energy and usually surface area to achieve, but the technologies are there to do it. The Gates Foundation, however, as part of their sanitation initiative, had a really constrained need for sludge dewatering. When they're emptying the pits, they have a small space on the back of the truck, a limited energy supply, limited cost, and it has to operate at 3 litres a second, right? We've invented a system that uses the pit emptying hose itself, because there's not lots of nice surface area there, and a really simple, elegant approach that doesn't use any flocculants or any other sophisticated systems that are typically used in order to do that. I'm so excited because when I get back to Seattle, we're just about to start doing the bench prototype for them. This is a bit of a shout out. It's a little bit different. So Zenova, I just need to explain, a lot of our ability to connect with these incredible companies and organisations around the world is through our partnership with Zenova. Zenova is an open innovation platform. They've assembled a network of innovators like us together with the needs for innovation, so the Pepsis, the Hondas, the GEs, and connected it all together in a really elegant way. There are quite a few open innovation platforms. And as an invention consultancy, we've tried them all, but we almost always exclusively do open innovation platform through Zenova because they have dialed it in really quite well. They've got global offices, including here in Australia, and have assembled a really interesting network of people like us who supply the solutions. This is the last one I just wanted to talk about. This is me breaking the rule about not going too far up the value chain because I see this opportunity. I want to go all the way with it. So this started as a project with a large agribusiness in Latin America that has a very large tomato growing operation. We did a value chain analysis for them, and I was astounded by the cost of the box that they have to put the tomatoes in to get it to market. Something like 10 to 15% depending on what species they're packaging. And when I dug into it, I understood why, right? Cardboard is a long, complex value chain itself, right? You have to grow the trees and make the pulp and make the paper, make the cardboard, make the box, transport in between all of that, middlemen, all sorts of stuff, right? So it's not surprising that it costs so much. I often say I get paid to ask the dumb questions. When I was doing this, I said, well, why don't you just use the biomass that you're clipping from the vines to make the box on farm? And it was sort of an epiphany that we all had. Is that possible? How would you do that? So we've spent the last several months in the lab. We came up with a bunch of different strategies. Most of them worked as strategies, but we've honed in on one that is the simplest and most elegant way to take a mixed biomass input and process it in a certain way that is able to produce a robust material that you can form into all sorts of structures, right? This material it's really nice, it's distinctive, it looks like you would expect a biomass box to look like. It works with a lot of different inputs. We've become very familiar with the produce section at the supermarket because I ran out of tomato stems from my garden pretty early on. The material is strong, it's light, it's waterproof, and most importantly, the process that we've come up with is really inexpensive. And so this has the potential to really deliver a triple bottom line, right? The economic advantages to being able to take a waste stream on farm and produce packaging on farm and deliver that value to the farmers is going to be a significant economic advantage, but it will also reduce the environmental footprint associated with the packaging, and more importantly, provide alternative employment opportunities in rural areas. I think that's pretty enticing and interesting as well. We're currently working on raising the first round of funding and spinning this off so that we can take the initial prototyping and development and work up a pilot plant to then demonstrate the economics and hopefully the market traction for this concept. So that's us in a nutshell. Again, thank you for this opportunity. This conference is really impressive, and this industry is really impressive. The way that you all embrace innovation and seek to do better for the world, and I hope we get plenty of chances to work together. So, thank you.